Thank you very much for the invitation to give this talk today. Today I'll be talking about metrics of constant Chern scalar curvature. So here we have the general outline. So the goal of this talk is to eventually get to the point where we're going to be discussing the existence theory for these non-Kähler canonical metrics. But for the first half of the talk, we'll start in the Kähler setting. So here we'll talk about some examples of constant scalar curvature Kähler metrics, and then their existence problem, all in the Kähler setting. And of course, also the Yao-Tian-Donaldson conjecture. And then we'll move into talking about estimates proved by Chen and Cheng, along with a continuity path that can be used to show the existence of a CSC metric. And then from there, we'll move into talking about how this theory can be generalized to the non-Kähler setting. So here, we can in fact prove the same estimates or similar estimates in the case of non-Kähler metrics. And then we'll, if we have time, we'll go over a proof, an outline of the proof of these estimates. Okay, so here we have some general setup. So we're going to be working with compact complex manifolds. The first half of the talk will be Kähler, the latter half of the talk will be non-Kähler. So we'll refer to the manifold as X, and then J is the pedal integral structure, and omega is this real 1-1 form, which we can also write out in terms of the metric Gij bar. And so this Gij bar is also referred to as the permission metric, and this is going to be a positive definite permission matrix. And then in the case where this real 1-1 form omega is closed, so if d omega is equal to 0, then this metric omega is referred to as Kähler. And so in the Kähler setting, everything's very nice. It's like the ideal complex setting to work in. But of course, it's has certain limitations. And so our goal here is to see whether this theory can generalize, weakening this Kähler condition. So here we have the Ricci form. So in the Kähler setting, the Ricci form is given by negative dd bar log determinant of g. And so it is also a real 1-1 form. And in the Kähler setting, no matter how you trace the Riemann curvature tensor, you always get the same Ricci because you have very nice symmetries in the indices in the Riemann curvature tensor in the Kähler setting. But in the non-Kähler setting, you can actually get 4 different Ricci curvatures arising and 2 different scalar curvatures arising. So for the latter half of the talk, we will restrict ourselves to the case where we're working specifically with this Chern Ricci form, so that it has the same, it's given by the same equation. And then also the first Chern class is defined to be the Deleuze homology class of this Ricci form. And by the dd bar lemma being in this class, the same thing as just adding dd bar, some smooth function phi, we'll see later. And the Chern scalar curvature is the trace of this Chern Ricci form. And so again, in the very convenient setting where the metric is Kähler, the Chern and Levi-Civita connections agree. And so all of the Ricci curvatures are the same, and you only have the one scalar curvature. But in the non-Kähler setting, as we'll see, like loosening the assumption that this metric omega is closed, it's possible to have 4 different Ricci curvatures and 2 different scalar curvatures. Okay, so now we'll talk about the story of canonical metrics in the complex or in Kähler geometry. So Calabi defined the Calabi functional as the L2 norm of the scalar curvature, which you can rewrite out as this like normalization, this L2 norm of the scalar curvature minus the average scalar curvature plus this correction term. And it can be shown that in this Kähler setting, the average scalar curvature is an invariant of your Kähler class. It comes down to being an invariant. It only depends on your first Chern class and then the Kähler class of omega. And so Calabi's goal here was, given a Kähler metric omega, finding a canonical representative inside that Kähler class, to which to represent the class. And so you want this representative to have nice properties. And so in this case, he defined extremal metrics to be critical points of the Calabi functional. And so you can solve the Euler-Lagrange equation and see that that coincides with like the grad 1,0 part of the scalar curvature being a holomorphic vector field. And then more specifically, a constant scalar curvature Kähler metric is one that satisfies that R of omega is equal to the average scalar curvature everywhere on X. And so you can see from the above equation, of course, this Calabi functional is going to be minimized when R of omega is equal to the average scalar curvature. As the second term here, this last term is an invariant that you cannot is going to stay the same regardless of which metric in your class you're choosing. And the only part you can control by varying the metric within your Kähler class is this first part. And so you can see that then CSCK metrics are minimizers of the Calabi functional. Okay, so here I'll just go over some general examples. The best known CSCK metrics are the Kähler-Einstein ones. And so these are the ones that satisfy that the Ricci form is, scalar multiple of the metric omega. And so up to rescaling, like the Ricci curvature doesn't change under rescaling, whereas the right-hand side does. We only have to assume the 3 cases where this lambda value, this constant, is either taking on like the negative case, so we can just reduce it to the -1 case, the 0 case, or the +1 case. And so in the +1 case, the Fubini-Sudi metric on complex projective space is the standard example. And then in the lambda equals 0 case, this gives you the whole family of Calabi-Yau metrics. So like complex tori, things like that, those are all admit Calabi-Yau metrics. And then for the negative lambda case, you can take an example to be like on Riemann surfaces of genus greater than or equal to 2, you can take the hyperbolic metric on those, and that will have, it'll be a Kähler-Einstein with -1 as lambda. And so if you are a Kähler-Einstein metric, then you are a subset. You're also a CSEK metric, and the CSEK metric falls into, seeing as it's a minimizer of the Calabi functional, it falls into also being, of course, a critical point of the Calabi functional. So this is the general hierarchy of these canonical metrics. And so there have also been explicit constructions of CSEK and extremal metrics done by Calabi, Huang, Guan, Tennyson-Friedman, Huang-Singer, and Apostle of Calderbank, Godeshan, Tennyson-Friedman. So that they're constructing instances of CSEK metrics that are strictly not Kähler-Einstein, as well as extremal metrics, which are strictly not CSEK. You have all tiers of these metrics, I guess in certain cases, explicitly constructed. Okay, so we will talk now about the existence theory for Kähler-Einstein metrics, because the Kähler-Einstein metrics are by far the most studied of the canonical metrics, I guess, in Kähler geometry. And so the Kähler-Einstein manifolds, so it does, add a pretty strong condition on the first Chern class of the manifold. Right? Because if your first Chern class, if you are to be a Kähler-Einstein manifold, then your first Chern class is going to be proportional to some Kähler class omega. And so that basically restricts to the case where the first Chern class is either strictly positive, equal to 0, or strictly negative. But there are tons of manifolds that don't fall into these 3 categories, and those manifolds just won't be able to admit any Kähler-Einstein metrics. And so the existence problem for the Kähler-Einstein metric was shown by Aben and Yau to be equivalent to finding an explicit solution phi solving this second order nonlinear PDE, this complex Monge-Ampere equation.
Hey, just a second. We lost actually we lost for the moment the connection. We can't see. Oh, okay.
It's back.
Yeah, it's back.
Okay. Did you lose like a? Should I go back?
We just lost. We couldn't see the slides anymore. I mean, now we're seeing it again. Yeah, but I don't think we lost anything of what you were saying, though.
Okay. Okay, that sounds good. So yeah, so solving for the existence of a Kähler-Einstein metric on one of these Kähler-Einstein manifolds comes down to finding a phi solving this complex Monge-Ampere equation, where this little f is the C-infinity, a smooth function representing the Ricci potential, and the phi is the solution that we're seeking, and the lambda is comes from whatever case you're trying to work out. So in the case where lambda is -1, so the negative first Chern class case, the existence of a Kähler-Einstein metric belonging to negative C1 of x was proved independently by Yau and Elben in 1978. And then in the case where lambda equals 0, so this is a Calabi-Yau case, this is sort of why, it's exactly why it's named now Calabi-Yau, that Yau showed the existence of a Ricci flat Kähler-Einstein metric omega in any given Kähler class. And this, I guess, yeah, also in 1978. And so this is the statement's a little different because this means that if you're working in the case where C1 of x is equal to 0, given any Kähler metric, you can always find like a Kähler-Einstein metric lying inside that given metric's Kähler class. And so when lambda equals 0, being Kähler-Einstein is also referred to as just being Ricci flat, because in that case lambda is 0, so Ricci of omega is going to be equal to 0. Okay. And of course, it's well known that the positive case, so the case where the first Chern class is positive, is by far the most difficult. And so the Yau-Tan-Donaldson conjecture, in this case, for Kähler-Einstein metrics, asserts that this algebra geometric notion of case stability is equivalent to the existence of a Kähler-Einstein metric. And so the forward direction was established by Chen, Donaldson, Sun in 2015, building on work by Tian, Yau, and Tian in the case of Fano surfaces. So Fano, sorry, is another word, just way of saying a manifold with positive first Chern class. So all of this YTD conjecture stuff is in the setting of Fano manifolds. And the reverse direction was shown by Tian, Donaldson, Stopa, and the most general form by Berman in 2016. And so this notion of case stability, I guess, was inspired originally from the moment map picture of like coming from geometric invariant theory in the finite dimensional case. Okay, and so how can this theory be extended to CSCK metrics? Right, so in the Kähler-Einstein case, the cases of lambda 0, lambda -1, you can find by solving the complex Monge-Ampere equation. For the lambda equals 1 case, it's a bit more difficult. You have to then study case stability. And then for CSCK metrics more generally, it's a conjecture by Yao, Tian, and Donaldson that the existence of a CSCK metric in a given Kähler class is equivalent to this relative notion of case stability. So here you're looking for one in a given Kähler class versus in the Kähler-Einstein case, you're looking for one inside that reach the first Chern class. So this is.
Sorry, what's CSC constant scalar curvature? Is that what it stands for?
Yes.
Oh.
Sorry, yeah, CSCK is constant scalar curvature. Kähler, I guess the word metric is missing. Yes, the word metric in here. And so it is known that the existence of CSCK, so the direction of existence implying case stability is the easier direction. So this one was discovered by Stopa or proved by Stopa and Berman. And then Donaldson proved this conjecture in the case of toric surfaces. But the converse, so the more general case of the converse, so like case stability implying the existence of a CSCK metric in a given Kähler class remains open. And so this problem is more difficult, both I guess from the case stability point of view as well as from the PDE perspective, because at least from the PDE perspective, it's a fourth order PDE, whereas the Kähler-Einstein metric is a second order PDE. And so once it's fourth order, you lose the ability to apply maximum principles and things like that. So a lot of the basic things that you can do for Kähler-Einstein, like for showing uniqueness, all of that theory no longer quite holds the same way in this fourth order PDE case. However, in work by Chen and Cheng in 2017 and 2018, they made significant progress towards answering this question. So they in fact will find in a condition that is equivalent to the existence of CSCK, but they haven't perfectly tied it back to this case stability notion. So, sorry.
This is very different to the Yamabe problem?
Yeah, so the Yamabe problem is looking for a constant scalar curvature metric inside a given conformal class. And this one is looking for one within the given Kähler class. It's like up to addition of dd bar phi. Okay, I'm having some technical issues on my side. Is my screen still showing?
Yeah,
Yeah, but it's stuck.
if you want, I can stop your screen share for you.
Okay, I'll reset it. Sorry, my laptop's a little slow today. I think my preview keeps crashing. Okay.
Do you have other programs in the background you can get out of? Or?
Yes. Sorry about that. I mean, I've closed as many as I can. Yes. Oh. We'll try Adobe. Okay. How's that looking? Okay. All right. Sorry about that. Okay. So yes, the goal here now in the Kähler setting is to discuss the existence of a CSCK metric, and so you're looking. So given some metric omega, you're looking to find another metric equaling omega plus dd bar phi. So you're really searching for the existence of such a phi for which the omega plus dd bar phi is another Kähler metric that is CSCK. Okay, so before we get into the existence theory, let me just quickly mention an obstruction to existence of a CSCK metric. So if we have that this underlying R represents the average scalar curvature of omega over X, then it follows that since it integrates to 0, there must exist some H for which the Laplacian of this H with respect to this fixed Kähler metric omega is going to equal to R minus underline R. And so then the Futaki invariant is an invariant that takes, given a Kähler class omega, it takes in a holomorphic vector field that needs to be representable in the form of, this holomorphic potential F. And so f of v is defined to be negative the integral of this vector field v acting on the h being h satisfying that the Laplacian of this h is equal to R minus underline R. And then so through an integration by parts, it comes out to also equal R minus underline R against this holomorphic potential F. And so it can be shown that f of v is an invariant of the Kähler class. So it doesn't change up to addition, the metric up to addition of dd bar phi will have the same f of v quantity. And so from here, you can see that if f of v does not vanish for some v, then that's an obstruction to existence of a CSCK metric inside the Kähler class of omega. Because if there were one inside it, then for that omega, that R minus underline R would go to 0. Right. And it's an invariant of the class. So the contrapositive gives you the statement. Okay. Now I'll talk about, but in the Kähler-Einstein case, Alban and Yau, in solving the second order, nonlinear, the complex Major-Ampere equation, used a continuity path. Here in the CSCK setting, like I mentioned, it is a fourth order PDE now, but the method used by Chen and Cheng is also to use a continuity path. And in general, when you have a very difficult PDE to solve, it's a common technique to apply to prove it using a continuity path. So in a paper in 2015, Chen proposed the following continuity path. So given some metric omega, you have this parameter t, which is a path between 0 and 1, is a number between 0 and 1 that connects two different PDEs. So at t equals 0, you start off with the second order PDE, a trace of omega with respect to omega phi equal this constant, that is just the normalization constant that you need. And then at t equals 1, we have the full-blown CSCK equation, right? That this R omega phi be equal to a constant. So the equation that we want to solve is the endpoint, the t equals 1 case. The equation that we know how to solve a priori is a t equals 0 case. And then by openness and closeness, we want to show that this, solutions exist everywhere. And so again, we're looking for an omega phi equaling omega plus dd bar of some smooth function phi that will depend on t. So this is how you, all metrics inside a given Kähler class, or in the Kähler class of this metric omega, is just going to be equal to omega plus dd bar phi for some smooth function phi. So it comes down to finding the phi. And of course, you can, dd bar constants is 0, so you want to also normalize your phi if you want to make it unique. Okay, so if we let I be the, subset of t in 0, 1, for which this equation sub t, star sub t, has a solution, then we can show existence of a CSCK metric omega phi if we can show that I is non-empty, open, and closed. So for the non-empty case, you can take phi equals 0, right? So to solve the t equals 0 case, you just want trace of omega with respect to some other metric in your class to be equal to a constant. So you just take omega phi to also equal to omega. Their trace will just be n, which will be the desired constant on the right-hand side. So we have a solution at t equals 0 along this continuity path. And for openness, in the same paper where Chen proposed this path, he was able to show openness for t away from 0. And so away from 0, you have this fourth order contribution. And so the path, it remains fourth order. However, if you start at t equals 0 and you want to show openness at t equals 0, you're jumping from a second order PDE to a fourth order PDE. And so that presents some additional challenges. So in later work by Hashimoto, Hashimoto and Zheng, using more sophisticated approximation methods, they were in fact able to show openness for t equals 0. So together, they've been able to show openness along this whole path. And then most recently, and generally speaking, the most difficult part of using a continuity path is showing the a priori estimates needed to get closeness along the path. So in work by Chen-Cheng in 2017, they show the a priori estimates under the condition of bounded entropy along the path. So you don't always have closeness And this is not surprising because you also don't always have existence of a CSCK metric. The condition they found that ensures the a priori, like, uniform estimates that you need for closeness comes from, as long as you have bounded entropy along your path. So entropy is given by law.
Is the entropy a definition just for that integral, or has it actually got some interpretation in terms of dynamical or some other entropy?
I think it's just a name for this integral.
Okay.
And it also, yeah, so we'll get into it later, and I possibly in the next few slides. This term is the first term in the Mabuchi K energy. So it's a primary component of Mabuchi K energy. I think it's just a name. Yes. Okay, so here we will now move into the strategy that Chen and Cheng used to show the a priori estimates. So you're looking again for some omega phi equaling omega plus d bar phi, that is CSCK. And so to do that, you want to obtain, I guess, all higher order, you want CK bounds on phi, depending on constants, like bounded by constants depending on phi, sorry, on K. Okay, so we'll get through it. So it's a fourth order PDE. And so to study a fourth order PDE in terms of trying to obtain estimates, there's just a lot happening at once. And so the strategy used by Chen and Cheng was to break the fourth order PDE into 2 second order PDEs. And then you can, once it's set up in a second order way, you can kind of piecewise do some of the estimates and then bootstrap it together to get the desired results. So what they did was they defined this auxiliary function f to be log of omega phi to the n over omega to the n. So the second order in the sense that this term is just like omega plus d bar phi. It's a second order in phi. And then f is just something that we're defining, it makes sense in the context of this coupled second order equation. And so then the next line is to take the Laplacian of f with respect to the metric omega phi. So I'm just annotating this by delta sub phi. And here we impose the CSCK equation. So when you take the Laplacian of f with respect to omega phi, the first term that comes out is negative the scalar curvature of omega phi. So here you assume it's CSCK, you force the CSCK equation by then just calling this r of phi underline r instead. And then the other term that comes out when you take the Laplacian is just this last term, which is trace omega phi of each omega. Okay, sorry, the notations aren't perfectly consistent. But when I put sub phi, I just mean sub omega phi. And this is also just second order in phi because you're just tracing over something that is dd bar omega plus dd bar phi. And so that's the strategy that they used. And so they, like I mentioned, they prove closeness under the assumption of this bounded entropy quantity. And the estimates that they show specifically are that if you have x and omega phi, a CSCK metric, where omega phi is equal to omega plus dd bar phi, then all derivatives and the sup norm of the Kähler potential phi can be estimated in terms of an upper bound of the entropy. So it's, I guess, more specifically, like the CK norm of phi is bounded by a constant depending on x, k, omega, and the entropy quantity. And once you have these a priori estimates, you can use them to prove closeness of that continuity path on the last slide. Okay. So the statement they make, so what they showed is in fact, bounded entropy implies closeness. And then with the other pieces that were shown previously, that implies existence of a CSCK by being able to solve through the continuity path. But they also relay their result in terms of properness of K energy, of this Mabuchi K energy. So here we have this giant equation, but you can observe that the first term in it is the entropy quantity. And the other two terms can be controlled, can be bounded in terms of the D, this like L1 geodesic distance. And so the statement they can in fact make is that properness of this Mabuchi K energy in terms of L1 geodesic distance in the space of Kähler potentials then implies the existence of a CSCK metric. And so the reverse direction was done in previous work, or in work in 2016 by Berman, Darbash, and Liu. So now we have a perfect statement about like the necessary and sufficient condition you need to show existence of a CSCK metric. It just hasn't perfectly solved the Yao-Tian-Donaldson conjecture because it's not in terms of this, this K stability. It's still just in terms of properties of K energy, but it's a huge step forward to understanding the existence of CSCK. So now we will move into, so we're roughly at the midpoint. So now we'll move into talking about how this theory can be generalized to the non-Kähler setting, right? So in general, a Kähler manifold is one that admits a Kähler metric omega, and this Kähler metric omega satisfies like d omega being closed. And so there are many obstructions to manifolds being Kähler. So for instance, if your first Betti number is, or your second Betti number, sorry, is 0, then you can't have like a 1-1 form that is closed, right? And so there are many examples of non-Kähler complex manifolds. For instance, the Hopf surface is diffeomorphic to S1 cross S3. So it has nothing in B2, and so it is non-Kähler. There are other non-Kähler manifolds like Inouye surfaces and other things that are non-Kähler. And also this theory is interesting because even taking a Kähler manifold, you know, the majority of the metrics on a Kähler manifold you can think of as just being non-Kähler Hermitian metrics. Or I'm not sure how you want to quantify them, but in general, you can always take Hermitian metrics on any manifold and then ask questions about one such, like when canonical metrics inside a class of non-Kähler manifolds exists.
You're still looking for constant curvature or something else?
Yes. So you can ask questions about extremal metrics, constant curvature. You can't ask the Kähler-Einstein question because the Kähler-Einstein condition. Well, you sort of can. So you can't ask the Kähler-Einstein question for Fano, like when C1 of X is positive or C1 of X is negative. That already implies that X is.
But I guess if you really relax everything, you go back to Yamabe.
You're not working with the conformal, like you're not.
You don't want to ask that question. Okay.
Oh no. So in the non-Kähler Hermitian setting, I will address this Chern-Yamabe generalization of the Yamabe problem.
Okay.
Yes. So yeah, there are many ways you can like consider these canonical metrics. So yes, here the question is from this, like what a natural question would be, like to what extent can this theory for existence be extended to non-Kähler Hermitian metrics? And so I guess implicitly this is saying this like the constant scalar curvature case. Okay, so here we'll talk about briefly some constant Chern scalar curvature metrics. So now I add the word Chern to it because in the non-Kähler setting, you can have two different scalar curvatures depending on how you're tracing the indices on your Riemann curvature tensor. And the one that I'm focusing on here is the Chern scalar curvature because it arises as the trace of the Chern-Ricci form that is desirable for our purposes because it can be represented as negative d bar log determinant of G. So you can, there's like complex Monge-Ampere equation sort of arising when you choose this Ricci. Whereas if you chose one of the other three Riccis arising in the non-Kähler setting, it just behaves very differently. And so there's another one that's called the second Chern-Ricci form, and that one also has received some attention, but I think the last two are just very difficult to work with. So those ones haven't really been too studied. Okay. And so one example of a constant Chern scalar curvature metric is just the standard round metric on the Hopf surface. So this metric is constant Chern scalar curvature. And here, a natural question of generalizing these things to the non-Kähler setting, of course, in this case also arises for the Yamabe problem. The Chern-Yamabe problem was investigated by Angela, Kellerman, and Svati. And so it's the problem of showing existence of a constant Chern scalar curvature metric within a given Hermitian conformal class. And so they were able to show existence in the case where the expected constant Chern scalar curvature is non-positive. I think in general, the positive case, so the positive case is still open. They weren't able to show or conditions for existence in the case where the expected constant Chern scalar curvature is positive. That's still open. And then in a paper in 2019 by Koch and Lejmi, they explicitly constructed some constant Chern scalar curvature metrics on ruled surfaces. And so this is sort of a motivating example. So specifically on these Hirzebruch surfaces, which are Kähler, that are known to not admit, Hirzebruch surfaces specifically of non-zero degree, they're known to not admit any CSCK metrics. And on these surfaces, Koch and Lejmi were able to construct like constant Chern scalar curvature metrics, which is like in the absence of having a CSCK metric, the next best thing you can do if you want the canonical metric, is to look for constant Chern scalar curvature metrics. Okay, so back to our problem of working within, like generalizing the Chen-Cheng result, which is working within a given Kähler class when we're discussing the Kähler setting. So in this case, we no longer have these Kähler classes because we don't have closeness of the metric, right? So once you take away the Kähler condition, like omega is no longer closed. So omega does not define like a cohomology class anymore. But you can still ask the analogous question of a constant Chern scalar curvature metric differing from a given permission metric. Up to addition, by addition of dd bar phi for some smooth function phi. So we're just mirroring the Kähler class case as closely as possible, but we are now working without the assumption that the metric omega is closed, and hence this metric omega now is not closed and also does not define a Kähler class anymore. And then, like I mentioned, we have to now specify which scalar curvature we want to work with. So the natural choice here is a Chern scalar curvature. Just by the way the estimates work out, again, referring back to the fact that the first Chern Ricci form is the nicest to work with, or it comes up and, its definition being negative dd bar log of the volume of the determinant of G is very essential ingredient in the proof of the estimates. So we held on to that. Okay, so the question we like to answer is, if we have X omega, a compact complex manifold, right? Under what conditions does there exist a constant Chern scalar curvature metric of the form omega phi equaling omega plus dd bar phi for a smooth function phi? So we're asking a very similar statement to the Kähler setting, but we are loosening the condition that omega be closed. And of course, this is the first pass in understanding these non-Kähler canonical metrics. You could ask it for the other scalar curvature and things like that, but the estimates would follow through most similarly in this setting. So this was what we did first. Okay. So in the absence, so the same estimates hold, in fact. The estimates hold under the assumption of bounded entropy. And in loosening the Kähler condition, right, things really get like hairy really quick, because the Kähler condition gives you many nice properties. Like, it gives you that you can do integration by parts in the standard way, and it gives you that you can commute covariant derivatives and move around indices in your curvature tensor a certain way, or freely, without picking up torsion terms, which are things that basically measure the inability of a metric to be Kähler. So in the absence of the Kähler condition, the estimates would be very tricky to follow through if we didn't still sort of have something that would allow us to control, the integration by parts and just like a certain invariance of the metric. So the assumption that we will make in this case is that dd bar of omega k be 0 for k equals 1 and 2. So this is strictly weaker than the Kähler assumption in general. And what we need it for is that it gives us the volume is preserved in the class. So if you integrate omega plus dd bar phi to the power of n, this assumption is the weakest one you need to ensure that when you try to integrate the stuff out by parts, you can get rid of the dd bar phi part, and so that this integral still ends up equaling the integral of omega to the n. So the volume shows up in a lot of the estimates. And so if your volume is running around with the phi, right, as a function of phi, there's just a lot more chaos in controlling what's happening. So it might still be possible. You might need additional, the estimates may hold under stronger assumptions or things like that. But for our purposes here, this was the weakest condition we can make to sort of clean up the really bad part in the estimates. And so the other thing that it gives you by the same line of reasoning is that the average scalar curvature is invariant, like working within this dd bar class, right, of a given permission metric. So again, if without this assumption, your average scalar curvature will also be running around as a function of phi. And so there's just more to have to control. And then finally, the dd bar omega to the n-1 condition, the Go-Duchamp condition, is one that allows you to say that the integral of a Laplacian is 0. So if you didn't have...
What are the examples which are not Kähler where this is satisfied your...
Yes, so that will be on the next slide. Okay, so yes, the condition may seem mysterious. So the fact that, so the condition that dd bar omega to the k equals 0 for k equals 1 and 2 is in fact the same as saying that the same thing, dd bar omega to the k vanishes for all k. So these are the synonymous statements, but they definitely can exist. So in the case of complex surfaces, so if n is equal to 2, a Gödel metric is one that satisfies a dd bar to the omega to the n minus 1 equals 0. So in the case where n is 2, a Gödel metric satisfies this condition. And Gödel metrics always exist by this theorem of Gödel, which states that, you know, on a complex manifold, give every Hermitian metric is conformal to a Gödel metric. So if you're working.
Can you tell us what a Gödel metric is?
Yeah, I should have written it. I'm sorry. It's that dd bar omega to the n minus 1 equal to 0.
Ah, okay, okay.
Yes. Yeah, I should have maybe put that in this theorem statement. So yeah, so when n equals 2, our condition here reduces to just dd bar omega equaling 0. And then dd bar omega equaling 0 is a Gödel metric will satisfy this condition in the case of complex surfaces. And so then another way to maybe find other examples, so this is very elementary, is to take your strictly non-Kähler complex surface and cross it with a Kähler manifold, and then the resultant product metric will be strictly non-Kähler because of the fact that you're crossing part of it with this non-Kähler manifold. And then taking the Gödel metric on the complex surface part with the Kähler metric on the Kähler part, this product metric will satisfy the desired condition. So yes, there aren't a plethora of examples per se, but there is another theorem by Fino and Tomasini in 2008, which tells us that this condition that we're studying here is preserved under blowups, basically. So if your manifold admits a metric satisfying this condition, then if you blow up at a point or you blow up along a complex submanifold, the blown up manifold will also admit a metric satisfying this condition. So you at least have some of these examples to work with. Okay. All right, and so we'll move now into the specific estimates. So what we can show in the non-Kähler setting are the following a priori estimates. So if you have x omega here, a compact complex manifold with omega Hermitian metric satisfying the previously stated condition. So k equals 1 and 2, here I just explicitly written them out. And this omega phi is equal to omega plus dd bar phi. And if this omega phi is a metric of constant Chern scalar curvature, then we get these a priori estimates. So we get the CK bound of phi, so it's bounded above by a constant depending on k, x, omega, and the entropy quantity. So the entropy again is the same quantity as it was in the Kähler setting. So it's the integral of this log of the volume ratio, omega phi to the n over omega to the n, integrated against omega phi to the n. And so you can also show that in the case where omega phi is not CSEK, you can still get up to W4K bounds on phi, but now the right-hand side will depend on the C0 norm of the scalar curvature of R of phi. Right, so if R of phi was CSEK, then this was just underline R, so it's not really a dependence anymore. And then in that case, you can bootstrap and get all the higher order ones. But when you don't have that R of phi is CSEK, or sorry, constant Chern scalar curvature, then the best you can do with these estimates is W4K or C3 alpha on phi. Okay, and so I guess I can say maybe something else. So in the Kähler setting, of course, the Chen-Cheng estimates are very useful because they provided, this very nice necessary and sufficient condition for existence of CSEK metric. Their estimates can also be used, in fact, in a less interesting setting to show like long time existence and convergence of like the Calabi flow in certain instances. And so the estimates that we have here in the non-Kähler setting can also be used to prove like long time existence and convergence of an analog of the Calabi flow in this non-Kähler setting. Okay, so now in the last, I guess, 20 minutes or so, we can go through an outline of the estimates. So this next part, the line of reasoning we use for proving the estimates follows very similarly from the Kähler setting. And A major hindrance is just now the presence of torsion everywhere, right? So again, like I mentioned, torsion is 0 in the Kähler setting. In the non-Kähler setting, torsion, even non-zero torsions are appearing everywhere whenever you're trying to commute derivatives, whenever you're trying to integrate by parts, whenever you're trying to just like swap around indices of your curvature tensor to trace up to give you the correct scalar curvature, you pick up a lot of torsion terms. Okay, but we'll outline the overall strategy. So we represent again this 4th order PDE as a pair of 2nd order PDEs, right? Given the same way as by Chen-Cheng. And so here we're going to be working with the Chern's 3G curvature. And the strategy now is you start off by showing C0 bounds on F and on phi. So F is the log of this volume ratio. So you want to first show C0 bound on F, and that actually takes a lot of work. We'll have to use the ABP maximum principle. And then we also want to show C0 bounds on phi, which we can do using like uniform Holder estimates for the complex Monge-Ampere equation, or I guess uniform estimates, sorry, for the complex Monge-Ampere equation. And then from there, you can show a C1 bound on phi using like step 1, using the C0 bounds. So I guess I want to say that in step 1, the constant here, when you do the ABP maximum principle to bound capital F, you will have dependence on the entropy at that step already. And then once you have dependence on the entropy, that dependence gets passed along to these constants in the subsequent steps. So the entropy bound for entropy dependence was already in step 1. Then from step 2, you use step 1, and step 3 is showing an LP bound on trace omega phi.
No, we lost the. Oh yeah, it's fine. Sorry, we lost the connection for a second.
Oh, okay.
That's good.
It's fine.
Okay, yeah. So step 3 is showing this LP bound on the trace. And here the constant on the right-hand side will depend on P. And then finally, in the 4th step, we will use like an iteration argument to, in fact, show an L infinity bound on this trace by a constant that will, like, just some constant in this case, which will depend on X omega and the entropy. Okay, so now we will, and then once you have this L infinity bound, you can find that the trace the other way is also bounded. And once you have that the trace the other way is also bounded, you can use a bootstrapping argument using the 2 second order equations to indeed obtain CK bounds on phi for all higher order K, where the constants will depend on the K. Okay, so here I'll mention some of the noticeable differences in the non-Kähler setting, or notable differences in the non-Kähler setting. So torsion terms no longer vanish. And so they arise when you commute covariant derivatives and then integration by parts. So here I've just written it out in the form of the divergence formula. So the divergence formula for Kähler in the Kähler setting is just equal to 0. So you can move around this nabla sub I however you'd like at no cost. But here in the non-Kähler setting, when you try to integrate by parts by pushing around a covariant derivative to the other parts arising, you pick up these additional torsion terms. So TP sub PI is just the trace a certain way. So the torsion is just the difference between these two Stoffel symbols. Okay. So here we'll start with the C0 bound. So it's like interesting from a technical perspective. You're taking this pair of 2nd order PDEs, and you want to start here by showing a C0 bound on F and on phi. So I would say the most difficult part in the work by Chen-Cheng was the C0 bound on F. The C0 bound on phi kind of comes alongside it when you do what you want the maximum principle to act. So we'll go through an outline of it, and there'll be a lot of terms, but I'll just point out, highlight the interesting parts of it. So first, to clean things up a little bit before jumping in, we can normalize phi so that it's super 0, and we can normalize omega so that the volume is 1. Okay, so then in the Kähler setting, we then would we use Yau's theorem for the solution of this complex Monge-Ampere equation that we saw earlier to find a solution. I guess, we're going to define this auxiliary function and we're going to use it. And so in this non-Kähler setting, we don't have Yau's theorem because that was in the Kähler setting, but we have this precise analog of Yau's theorem, which is a result by Tassadi and Wynkow for complex manifolds. So the statement is that basically in the non-Kähler setting, you can still solve this complex Monge-Ampere equation. So for every smooth real valued function g on x, there exists a unique b and a unique smooth real valued function psi on x, solving this complex monotone pair equation. So this is very similar to the one in the Kähler setting, except now we have this little constant b, which I'll discuss. And so of course we're looking for the solution psi that satisfies that omega plus dd bar psi is still a metric. So we want that to still be positive. And we'll, psi is not normalized. And so to make it unique, we're just going to normalize it so that it's super zero. Okay, so in particular, if you have that the given metric omega that we're starting with satisfies the condition that I was talking about earlier, that dd bar omega to the k equals 0 for k equals 1 and 2, then the constant b must equal to this log ratio, which does not depend on psi, right? And so what that is using is the fact that if you integrate the left-hand side of this complex monotone pair equation and you integrate the right-hand side, you can isolate e to the b, and you use invariance, like the fact that volume is preserved under dd bar phi. So the integral of this left-hand side is just equal to the integral of omega to the n. So it's needed to remove the psi dependence. And once you remove the psi dependence, then you can just, divide out by the e to the g omega to the n integral part and get that the b must have been this constant. So in the case where you don't make this assumption, you can still solve this PDE, but the value for b doesn't really have any nice bounds on it going in, and it will depend on psi, which is kind of not the point. So you kind of get an entanglement in the case where you don't make this assumption on the omega. Because psi is the solution that you don't want the b to, I don't know. You don't want this dependence, it becomes very inconvenient. Okay, so from there, we're gonna let g, so we're gonna use that last theorem. So we're gonna let g be equal to f times log of the square root of f squared plus 1, which is roughly like an absolute value function of f. Then we'll let psi be the function solving this as per the result of the last theorem. So this, choosing g to be this thing, there exists a psi by the Sadi-Weinkoff result that tells us that omega plus dd bar psi to the n will equal to this right-hand side. And we'll start to see that this right-hand side the denominator at least, is basically the entropy quantity up to careful sign control. Okay, and then another piece of the puzzle that we need is Tian's alpha invariant. So Tian's alpha invariant gives you a very nice band, so I guess I'll just state it. So if you have x omega complex manifold, there exists constants alpha and c, both positive, depending only on x omega, such that for all psi for which omega plus dd bar psi is positive, you can bound the integral of e to the power of negative alpha against a normalized psi by a constant that doesn't depend on psi. So it just holds for all of these PSH functions. So all psi satisfying that omega plus dd bar psi is positive. So this gives you a lot of control. So this is a result that was proven in the Kähler setting, and I think in the literature not formally written anywhere, but the proof does not rely on the Kähler assumption. And so Tian's alpha invariant, in fact, also holds in the non-Kähler setting when you're still working with the dd bar, the addition of dd bar phi to a given metric omega. Okay, so then using this, we can show that we immediately have that for our phi and for our psi, they are both PSH. And so the integrals of both of these guys are bounded by this constant c. This uniform C. Okay, from there, we will apply the AVP maximum principal argument. So it gets a little bit more computationally involved here. So you're gonna let Q, so these are gonna be equal to E to the power of delta against F plus epsilon psi minus lambda phi. And so the constants delta, epsilon, and psi and lambda will be determined as we go, to offer us, I guess, yeah, the flexibility will be chosen along the way and chosen accordingly. Okay, so then you also need to choose a cutoff function, just be careful of behavior on the boundary. So I won't really go too much into that. Effectively, when you take this Q against this cutoff function and you take its Laplacian, and then you move one of the constants to the other side, you get the Laplacian to be bounded below by this thing. So delta, eta, all against negative constant, all of these things in the equation, which are hard to read out. And this I sub f is again the integral of e to the f root f squared plus 1. So this I to the F dependence arises here, and this I to the F is effectively the entropy quantity. Okay, from there, the ABP maximum principle tells us that once you've computed this Laplacian, then the sup of Q eta over a ball can be bounded by the sup of Q eta on the boundary of the ball, plus the negative part of this integral, effectively, with all these things inside it. And then you can use positivity of this root f squared plus 1 and positivity of this entropy quantity to then find that the negative part of this integral can be controlled in terms of this quantity integrated over the set where you're intersecting with f being bounded from above, right? And then cleaning that up further and using the fact that we've chosen, alpha accordingly, we in fact can get that this right-hand side is bounded above by constant C. And this constant C will depend on the entropy. So there are a lot of details that I'm bypassing here. But the idea is that, so you needed to, we chose root f squared plus 1 because we wanted positivity so that we could use this method. That's kind of why we chose this funny function. And then we had to strategically choose the constants and such, and also the alpha invariant so that this worked out this way. So it looks nice now, but I'm sure in the first pass when Chen-Cheng did this, they had to strategize there were probably a lot more terms going on before they were able to clean it up a little bit more. Okay, so once you have that, you can in fact show that, the sup of Q is bounded above by this constant C. What does that say? Because given the way that Q is defined, this upper bound then tells us that the exponent is bounded above by C. So this is a statement that F plus epsilon psi minus lambda phi is bounded above by C. So now we can see that we can bound F from above if we can bound phi and psi, right? So then using uniform estimates or uniform continuity of the complex Monge-Ampere equation for Hermitian metrics. So this is a result in the non-Kähler setting that was proved by Deneb and Klajic and Blotsky. It follows that given the way that they were defined, in fact, phi and psi are uniformly bounded. And so then that gives you an upper bound on F. And that was the main part of the work. And then a lower bound for F can be followed using a very simple and straightforward maximum principal argument. And so that gives you C0 bounds on F, and also on the way, we use this uniform continuity of complex Monge-Ampere equation to get the C0 bound on phi. And psi was just the function that we use in the interim that we don't actually really care about. Okay. So now I will probably breeze through this relatively quickly. So there's 3 steps remaining. Step 2 is the C1 bound. This comes down to choosing, I guess in all of these cases, when you're showing these upper estimates, the strategy is choosing the right quantity to which to apply the maximum principle. So in this case, I've had to adjust it a little bit from the Kähler setting because in doing, so there's been a lot of instances where you're going to want a Young's inequality, Cauchy-Schwarz, et cetera, away certain terms. You might need to boost up, give yourself more buffer in terms of having more good terms around to help control the bad terms. The bad terms being these torsion terms, right? So we're going into this knowing that the Chen-Cheng results like hold true and work out. And so the work comes down to controlling these additional torsion terms that arise now in this non-Kähler setting. So we've had to modify the quantity a little bit so that we can control the non-torsion terms. So if you then compute the Laplacian of this quantity, the red terms are the torsion terms. So you can inequality them into different forms. And in this case, you just have to, you want to bundle them into terms that are already arising in such a way that the constants are different, but not harmful to you. And so in this case, it actually comes out pretty straightforwardly. You can, once you put them in this form, so the torsion on the non-fixed metric omega phi can actually be passed to the torsion term on omega by a relationship by the way that they're defined. So once you pass everything in terms of a torsion on the fixed metric omega, then those torsions are bounded, and so you don't have to worry too much about it. So in this case, it actually works out nicely, and so you get the desired results. So the LP bound is similar. You have to adjust your quantity a little bit, so it's a little different from the Kähler setting. You proceed in the computation. You notice torsion terms arising, and you try to bundle them into already arising terms. So in this case, so you can do Cauchy shorts, or you can complete the square, in which case you don't waste as much, because sometimes it really comes down to just not throwing away, trying to hold on to as much of the good stuff as you can for as long as you can. In this case, we completed the square, got these two torsion terms, and then thankfully again, they get bundled nicely into already existing terms in the computation. So then to get the LP bound, you compute Laplacian, you basically come to a point. There's also an integration by parts at the control 4, but thankfully it's not so bad. And you get to a point where you can show that the integral of the traced with this higher power is bound above by constant times the integral of the traced with slightly lower power. And then once you have this, you can bootstrap it to get all higher order estimates, as long as you can show that a base case holds, right? And so yeah, this constant will depend on P. It's like how many times you iterate up, the constant might grow in power or whatever, and that's fine. So here we want to just make sure the base case holds. So in the case where P equals 0, this inequality turns into the integral of the trace to the power of 1 plus 1 over n minus 1. Whereas the right-hand side is just now trace, the integral of the trace straight up. And the integral of the trace you can actually write out as n plus Laplacian of phi. And so the Laplacian of phi, this integral vanishes by our assumption that omega is at least Gaussian. And then the integral of n is just some volumes. So we are done. That gives us the volume, the LP bound on trace. And the final step is iterating over the LP bounds to obtain an L infinity bound on the trace. So here we had to actually do much more in terms of generalizing it to the non-Kähler setting. And then it reduces to finding a solution to an ODE, I guess, two ordinary differential inequalities. And then once you have that, then you're able to use the same balancing act as was used by Chen-Cheng to control the good and the bad terms to get the estimates to work out. I'm sort of out of time. Okay, so here we have some next problems to think about. So all of this theory that, so we thoroughly covered today the theory of CSEK existence. And now, we want to generalize this to the non-Kähler setting. There are two different scalar curvatures you consider. The more natural choice for now is the Chern scalar curvature. So we can build out a program for proving existence of these constant Chern scalar curvature metrics. So the problem firstly is that we don't have a continuity path along which we can show openness, because openness, also a lot of the proofs in the openness requires like the inverse function theorem, checking like kernels of your operator, of the linearization of your operator. And so in general, when you do integration by parts in the non-Kähler setting, you keep picking up torsions everywhere. It may sound surprising, but it ends up kind of ruining a lot of the way it doesn't come out as cleanly, and so you can't make the same conclusions, at least in the ways that I've been trying it. But of course, if we are able to show openness, then we can start to establish more of the theory of like what conditions might lead to existence of a constant Chern scalar curvature metric. And so again, this entropy quantity, which is the one that implies the a priori bounds, we'll maybe also want to interpret from a geometric perspective. So in the Kähler setting, there's a lot of theory related to this entropy quantity because it is a main component of the Mabuchi K energy, which is a very well-studied energy functional in the Kähler setting, but not so much in the non-Kähler setting. And then similar to the Futaki invariant, so some immediate way of seeing an obstruction to existence, we really expect there to be many obstructions to existence of a constant Chern scalar curvature metric. So it'd be nice to study those. And then another result is that in the Kähler setting, if you have existence of a CSEK metric, you can in fact show that in certain directions that you have a neighborhood of CSEK metrics. So this openness condition also be interesting in the non-Kähler setting, but again, the integration by parts that arises when you try to use this inverse function theorem or implicit function theorem stuff becomes a little bit more wacky. Okay, and this last one, I guess I didn't really touch upon, so we can ignore that one. But this is really to the analog of the standard Calabi flow to the non-Kähler setting, whose convergence and long-term existence you can show using the estimates that I discussed today. Okay, so I'll end there.
Thank you. Questions?
So what's the I mean, you said that the closeness is somehow it follows from the boundedness. Yeah, I mean, bounding stuff by the entropy, but how is that related to K stability?
Oh yeah, so it's even in the Kähler setting, the bridge between the current like bounded entropy to K stability is not well understood. So this is still an open problem. If you can understand that bridge, then you'd be solving the YTD conjecture in full. Yeah.
So is that the main stumbling block? The openness is not an issue?
So are you referring to the Kähler setting?
I mean, yeah, let's say in the Kähler setting even.
Yeah, so in the Kähler setting, Chen-Cheng have established that existence of CSCK metric is perfectly equivalent to bounded entropy, or in other words, properness of the.
Oh, okay.
But like the original YTD conjecture wants to relate existence of a CSCK metric to like this relative K stability condition, like relative to your given Kähler class, and so that's still open in the one direction is still open. Like that K stability implies existence is still open. Yeah.
And what was, you mentioned, so what's the issue about openness in the non-Kähler setting? Is it that you don't understand the kernel of the linearization, or?
Yes, it's like all the integration becomes very bad. And so your linearization is the same, but then, you know, normally in the Kähler setting, you study like its kernel and things by just by integration arguments. And so here the integration arguments don't work. Yeah, I mean, yeah, this is surprising to many people. So I don't know, there are other ways that maybe you could try to bypass this problem, like instead of using, like maybe studying it from, I don't know, there's like other theory that could be used, but so far the torsion terms presence kind of like messes with them in all the cases. Like the other method is like instead of using that, you can use like a Lurie-Shatter type of estimate to try to see if you can show like openness instead that way, but it's still difficult. And yes, so that would be ideal if we could get that to work out.
I have a question. So in your setting, how stiff is the condition that you need a bound on the entropy? I mean, like is it something which like genetically achieved or something like that?
It is pretty stiff, unfortunately. Yeah. Yeah.
So if it is obstructed somewhere, you will also know that it's obstructed in the neighborhood of it. That's what you're saying.
Probably, yes. Yes.
Okay, so there does not seem to be any other questions. So thank you for the beautiful talk.